Okay. So, good afternoon, everyone. This is Ferdinando Nunziata, and I'm very happy to present the activities carried on during this ASI-funded project, whose name is APPLICAVEMARS. Actually, APPLICAVEMARS is the acronym. First of all, I would like to thank the working team that contributed to this presentation and to the project, and that consists of people from Università di Napoli Partenope, from CNR, Istituto di Scienze Polari and Istituto delle Scienze Marine, and CSIC, so the Spanish CNR, and in particular the Institute of Marine Sciences. So basically, at the very end, the goal of this project is providing high-resolution sea surface wind maps. So using satellite remotely sensed measurement, mainly collected by synthetic aperture radar. So first of all, let's have a look at why we are interested in sea surface wind. So basically, this sea surface wind is an important parameter from both scientific and operational viewpoints. You know, from a scientific viewpoint, just to mention a few applications, we can see that it's important for meteorological and oceanographic studies and so on. From an operational viewpoint, again, just to mention a few applications, you can see maritime traffic control. We can where the wind speed is a key driving parameter. So from an operational viewpoint, we have a number of tools, conventional tools that routinely provide measurement related to the surface wind speed. And in particular, we have buoys and high frequency radar that, you know, provide, in case of buoys, provide point-like information, since you know, the buoys are able to sample wind information at the point where the buoy is located. And high-frequency radar provides a little bit wider coverage, but you know, it's still quite narrow. So if we are interested in wide coverage estimates, so in a synoptic view of these geophysical parameters, remote sensing, and in particular space-based remote sensing, so satellite remote sensing is a key tool, and in particular one of the best tools is basically a radar. And in particular, this kind of radar, which is termed as scatterometer, is basically designed, is innovatively designed to estimate wind, the wind vector over the sea surface. And the key physical rationale is you know, consisting of linking the normalized radar cross-section measured by the scatterometer to the local wind through the sea surface roughness. So basically, when you have a flat surface, so there's basically no local wind. As the wind increases, you have the surface gets rougher. Of course, the things are a little bit more complicated, since you can also have a number of external factors that affect your roughness. But at least in principle, this is the rough picture. And you know, the scatterometer is actually able to provide very interesting synoptic maps, such as the one I'm just showing you, where you know, you have this wind vector estimates, sea surface wind maps, whose temporal sampling is very dense, since you can have two of this map for each day, and you also have a number of scatterometers that are actually providing this kind of measurement. So there's a very large number of wind maps over the sea surface. And the spatial resolution, this map, so those measurements, is actually around 25 kilometers or around 10 kilometers. It depends on the sampling adapted, but you know, it's tens of kilometers. So the question is this spatial resolution adequate for the application? You know, this question does not omit a trivial answer, because you know, if you look at your wife or at your husband, of course you don't care about the fact that we are all made of atoms. So you know, spatial resolution, finer spatial resolution is not always a key factor. But there are a number of applications where this finer spatial resolution is a very good point. In particular, this applies when you're dealing with regional scale applications. So if you are dealing with the estimation of wind vector in coastal areas or in general in regional studies, of course, the 25 or 10 kilometers provided by the scatterometers are not adequate. So the spatial resolution is too coarse. And you know, for the scatterometers, we have also the problem of sea-land mixing related to the poor spatial resolution. So in all this kind of application, it's important providing finer resolution maps. So the idea is, can we use another kind of radar? So the scatterometer is a radar, but it's not alone. I mean, there are a number of radars. And in particular, we all know that there is also another radar called a synthetic aperture radar. So it's a radar that adapts the so-called synthetic aperture technique and is known to be able to provide very fine spatial resolution normalized radar cross-section map up to the meter scale. So the question is, can we exploit this kind of radar to estimate the wind map? Yes, in principle, it's possible because it's a radar. But if you look at SAR basics, you may easily find that actually the problem is that radar SAR is not inherently designed to estimate the wind vector. So it's only able to provide one measurement for each resolution cell. So this means that the estimation of the wind vectors is inherently under the domain problem. So you need external information if you want to estimate the wind vector. So this is actually the motivation that where the work we are carrying on this Italian Space Agency funded project stems, because actually at the very end, the goal of our project is to develop or ameliorate a geophysical model function, so function that links the output of the SAR to the wind speed. So basically, they are empirical function, because you know the relationship between the sea surface roughness and the normalized radar cross-section is not at all trivial in terms of electromagnetics. This is also applies for the scatterometer. That's why there are a number of empirical functions that are used to link this the geophysical parameter of interest to the measurable. And the second objective is to cross-check this multi-frequency estimates using ancillary information that comes from scatterometer, model forecast, and also by buoys. So this is the Gantt chart about the planned activity. Yeah, the project just started in 2000 at the end of May. So basically we are in the very preliminary stage. So basically we just selected the area of interest. We selected 4 areas of interest, and we start collecting C-band, Sentinel-1, X-band, Cosmos Skymet, and Cosmos Skymet second generation, and also L-band data coming from the L-band SAR SALCOM. And we also have ancillary scatterometer and forecast data. So this is basically, you know, the rough picture of the data we start collecting. So with respect to the SAR dataset, we have a number of SIM that have been already collected. In particular, we have more than 300 data in the Mediterranean Sea, collocated with ASCAT and HY2 scatterometer. And we also have Cosmos Skymet, the first and second generation data. And this kind of part is still ongoing since we are acquiring new data. And we are also acquiring SALCOM L-band data. So the processing chain, we planned this one. So we started from the AVP polarized SAR imagery. Then there's a sort of pre-processing that consists of, you know, multi-looking, downgrading, the undersampling, and so on. Then basically we evaluate wind map by using a cost function that compares the measured normalized radar cross-section with the one predicted by geophysical model function that we stored in a lookup table. And if you have external wind information, we can estimate this wind map. Yeah, in this preliminary experiment, I'm just showing the GMF we are going to adopt in this kind of processing chain. So for the C-band, we selected the state-of-the-art C-band model function. So we have the so-called C-mod family. It is a family of C-mods coming from the scatterometer heritage. And then we also have the SAR mod, which is innately developed for SAR measurement. And in this first row, I'm just showing the normalized rate exosection against the so-called azimuth angle. So the angle between the SAR pointing direction and the wind direction, and the angle of incidence. And you can see that there are some differences among these three modes, this geophysical model function that especially applies when dealing with the azimuth dependency. And in the second row, we have the same plots, but at higher wind speed. So at 10 meters per second, here is 4 meters per second. Then we also implemented the state-of-the-art X-band geophysical model function, in particular the one X-mod2, which is operationally applied to estimate wind from the German TerraSAR-X satellite. And in red, we have the so-called Italian Space Agency version of this X-mod, so the ASI X-mod2. In this case, you can see that there are some quite large difference, in particular at its lower wind speed between this German TerraSAR-X geophysical model function and the Italian Space Agency one. Those differences tends to reduce when dealing with higher wind speed conditions. So let's move to the first experiment. So just a preliminary experiment carried on Sentinel-1 data. We just start processing those kind of data. So this is Sentinel-1 measurement collected on the 4th of November 2014. You can see that there's also an overlay with ACNWF in red and ASCAT in blue. So this is the estimation that is obtained using the C-mod family, so C-mod 5 and C-mod 7, and then here we have the SAR mod. You can see that basically the trend is pretty much the same. So there are some differences, but not too much among these three geophysical model function. And also the agreement with the ASCAT measurement is pretty much is fairly good. In this case, since it's just a preliminary test, we consider the same spatial resolution of ASCAT. So this is about 12 kilometers, and even in this case, the pixel is 12 kilometers. So in this case, we are not enhancing the spatial resolution of the SAR of the wind product, because it's just for reference purposes. Let me show another experiment. Here we are always in the Mediterranean Sea. Now we are between Corsica and the Mediterranean Sea, between Corsica and in the Italy coasts. The area is is a bit complex than the previous one. Again, we have some external wind information provided by ACNWF red and ASCAT in blue, and these are the maps. Even in this case, there is a fairly good agreement between the three geophysical model function, and even the agreement with the ACNWF. Here I showed the ACNWF just to let you know that we compared our estimation using both satellite winds and model forecasts. So in this case, we have the ACNWF, and you can see that there's a fairly good agreement between the variability between the map provided by the SAR estimation and the one predicted by the ACNWF. Of course, that the variability from you can see from the estimation is for sure larger than the one provided by the ACNWF as expected. So let's move to the conclusion. So basically, our goal, this Italian Space Agency funded project, is estimated sea surface wind field using multi-frequency synthetic aperture radar measurement. Collected by three satellite SARs, in particular the C-band Sentinel-1, the X-band Cosmos Skymed or Cosmos Skymed second generation, and the N-band SARCOM. We implemented this geophysical motor function, and we are now processing the data set of C-band Sentinel-1 measurement, and we are moving to the X-band case. And you know, in a very short time, we are also trying to address the L-band estimation, which is by far the most challenging one, since the accuracy of the L-band estimation is expected to be lower than the X and the C-band one. So this concludes my talk. So thank you very much.